Hey everyone, welcome back. Let's talk about another easy problem on Leetcode today. Climbing stairs, Leetcode 70. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are climbing a staircase where it takes n steps to reach the top. Each time, we can either climb 1 or 2 steps. Then our task is to count how many distinct ways can we climb to the top. And in example 1, n is equal to 2. So we have a staircase containing 2 steps to climb. Now one way can be that we climb 1 step and then second step, or we can climb 2 steps simultaneously. So total number of ways to climb to the top is 2. Similarly, for n equal to 3, we can either climb 1 step at a time, or we can climb 1 step till this point but then climb 2 steps, or we can also climb 2 steps and then climb 1 step. So in this case, there are total 3 ways to climb to the top. Even though simple, this is a good problem to practice and understand the concept of dynamic programming by breaking down this larger problem into smaller overlapping subproblems. Now in terms of solution, one of the naive approach can be to use a DFS or backtracking like approach. At each step, we decide whether to take 1 step or 2 steps and increment the step taken so far. And if at any point we reach exactly n steps, we count that path as a valid one. But if the steps exceed n, we will stop the recursion and backtrack to find another path. These two scenarios form the base cases for our solution. For example, for n equal to 4, we start with 0 steps. Now, we can either take 1 step or 2 steps. After taking 1 step, we can again take 1 step, making total number of steps as 2, or 2 steps. Similarly, from this point, we can again take 1 step or 2 steps. And here we have reached n equal to 4, so this is a valid path. Similarly, continuing from 3, we can either take 1 step or 2 steps. So this one is a valid path, but this one is not, so we will backtrack. And similarly, we will continue until we have found all the valid paths. Now the time complexity of this approach is O of 2 to the power of n, because at each step we are making 2 recursive calls. And the space complexity will be O of n, mainly coming from the depth of the recursion. But a slightly better way to solve this problem can be if we can break this problem into smaller subproblems. For example, let's solve for n equal to 4. Suppose we have already solved for n equal to 2 and n equal to 3, as we did during the example walkthrough. Then the total number of ways are only 2, where we can either take 1 step from third staircase, or we take 2 steps from the second staircase. Since these two routes to staircase 2 and 3 are distinct, the total number of ways to reach staircase 4 will be total number of ways to reach step 3 plus total number of ways to reach step 2. And this will hold for any generic n, where total number of ways to reach nth step will be total number of ways to reach n minus 1th step plus total number of ways to reach n minus 2th step. Now, unlike the backtracking approach, this recursive breakdown avoids enumerating all paths and directly focuses on combining distinct routes, making it slightly more efficient and simpler. For example, for n equal to 4, number of ways to reach at the top of the staircase will be sum of f of 3 and f of 2, which are number of ways to reach steps 3 and 2 respectively. Now to calculate f of 3, we go deep down further. So following the recursive definition, f of 3 will be equal to sum of f of 2 plus f of 1. And now we have hit the base case, where we know for number of steps equal to 2, number of ways is 2. Similarly, when steps is equal to 1, then number of ways is equal to 1. So total number of ways to reach step 3 will be 3. And again f of 2 is a base case here. So total number of ways to climb 4 steps will be 5. Now the time complexity of this approach is still O of 2 to the power of n because of overlapping subproblems which are computed multiple times. For example, let's take n equal to 5. Then this will add one more label to the recursion tree, as f of 5 will be equal to sum of f of 4 and f of 3. This roughly doubles number of computations due to redundant calculations. For example, even though we have calculated f of 3 here, we will be recomputing it. So because of these redundant calculations, the time complexity will be O of 2 to the power of n, and the space complexity of this approach is O of n due to recursion stack, which can grow up to n levels deep. Here is a quick code for recursive approach with Java code on left and Python on right. First we have a base case, that is, if n is equal to 1 or n is equal to 2, in that case we will return n itself. Otherwise, we first compute number of ways to climb n-1 steps and take one step forward, and then count number of ways to climb n-2 steps and takes two steps forward, and sum of the two results, which we will return as our answer. Now we see some problems like f of 3 occur multiple times. Similarly, f of 2 and f of 1 also occur multiple times. These are called overlapping subproblems, which occur when the problem can be broken down into smaller subproblems that are used multiple times throughout computation. And we also have optimal substructure, as we can combine the results of f of n-1 and f of n-2 directly to solve the original problem, which is f of n. And whenever we have overlapping subproblems and optimal substructures, this tells us that we can use dynamic programming here. Now we can solve this problem using top-down dynamic programming or the bottom-up one. And we can start with the easiest one, which is top-down dynamic programming, which uses memoization. Memoization is a technique where we store the results of the subproblems to avoid redundant calculations. It is like caching the result so that we can reuse it in other parts of the problem. So in the top-down approach, we start solving the problem recursively from the highest level. For example, here we start with n equal to 5. And then we save the results of the subproblems like f of 3 in the memoization table, which is essentially a data structure like a hash map or dictionary or array to store the results of previously computed subproblems. This way, we can reuse the saved result rather than recomputing it. For example, here we can use a map to store the results of intermediate steps. This helps us avoid redundant calculations. For example, we can calculate f of 3 here once and then reuse it later whenever we see that repeating subproblem. Now let's quickly see this in action. So suppose n is equal to 5 and we have already seen this recursion tree. So when calculating f of 5, it will be sum of f of 4 and f of 3. Now we go down further where f of 4 will be equal to f of 3 plus f of 2, and we go down further where f of 3 will be equal to f of 2 plus f of 1, and now we have hit the base cases where f of 2 and f of 1 return 2 and 1 respectively. So f of 3 will be equal to 3. So for f of 3, we will save result as 3 in the memo table. Continuing with our recursion, we know f of 2 will be equal to 2. So f of 4 will be equal to 5. So for f of 4, we will store the result as 5 in the memo table. Now continuing with our recursion, to calculate f of 5, we still need to calculate f of 3. But f of 3 is already present in the memo table. So we will reuse that result and return it to f of 5, which now can be calculated as 8. Now the time complexity of this approach is O of n, because all the subproblems from 1 to n are calculated exactly once, and the space complexity will still be O of n because of the recursion tree and this memoization table that we are using to store the results of the subproblems. Here is a quick code walkthrough using dynamic programming with top-down approach with Java code on left and Python on right. Here, first we create a hash map or dictionary called memo to store the results for previously computed values of n. Now this code logic is very similar to recursive approach, where we first check for the base case, that is whether n is equal to 1 or 2. In that case, we will return n itself. Otherwise, we will check if we have already calculated the value for n to avoid redundant computations. So if the value for current n is already present in the memo table, then we will return the cached value. Otherwise, we will recursively solve this problem for n-1 steps and n-2 steps and sum of the results and store that result in the cache for the future reuse. This ensures subproblems are solved only once. and in the end, we will return the calculated results. Now let's solve this problem using bottom-up dynamic programming approach. Because this method avoids recursion overhead related to function calls and minimizes space spent on the recursion stack. Also, for this problem, arriving at the bottom-up approach is quite intuitive. In this approach, we use tabulation, which involves solving all smaller subproblems first and storing their results in a structured table or an array, many a times called DP table. So for this problem, let's create a DP table of size n plus 1, as we need to compute the results for steps starting from 1 all the way to n. Now, in this approach, we start solving from the smallest subproblem. So we already know the values for f of 1 and f of 2, which are 1 and 2 respectively. These values are stored directly in the array as the initial base cases. Now, using the results of the smaller subproblems, we can compute larger subproblems systematically, moving sequentially from f of 3 to f of n using the loop with iterator, say I. So for I equal to 3, number of ways will be f of 2 plus f of 1, which will be equal to 3. Similarly, for I equal to 4, number of ways will be f of 3 plus f of 2 equal to 5. So if you observe carefully, we are solving the problem for the current number using the sum of previous two numbers. So for the ith number in this DP table, we can write it as dp of I is equal to dp of I minus 1 plus dp of I minus 2. And this is what we call DP recurrence relation. Now continuing with I equal to 5, number of ways f of 5 will be equal to f of 4 plus f of 3 equal to 8. And now since we have reached n equal to 5, we will return 8 as our answer. So given a staircase with 5 steps, there are 8 ways to climb at the top of it. Now the time complexity of this approach is O of n, since we calculate each subproblem from I equal to 1 to n exactly once. And the space complexity will be O of n for using the DP table of size n plus 1. Here is a quick code walkthrough of the bottom-up dynamic programming approach using tabulation with Java code on left and Python on right. Here again we check for base case, where if n is equal to 1 or 2, we return n itself. Note that we don't have to explicitly check for base case because they will be covered in the DP array initialization, but they help in improving the readability. Now let's create DP array of size n plus 1 to store the number of ways to climb each step. Let's initialize the base cases, that is dp1 and 2 to 1 and 2 respectively. Now we can iteratively fill the DP array by running the iteration from I equal to 3 to n using the recurrence formula, which is dp of I is equal to dp of I minus 1 plus dp of I minus 2. And once we are done with all the numbers, we will return dp of n as our answer. And now the question is, can we do better? And the answer is yes, at least in terms of space complexity. If you observe carefully, the recurrence relations for I steps is dp of I is equal to dp of I minus 1 plus dp of I minus 2. We only need the last two values, that is dp of I minus 1 and dp of I minus 2. For example, for I equal to 4, dp of 4 is equal to 2 plus 3 equal to 5. So all the older values beyond that are no longer required in the memory. This allows us to optimize the space complexity by only storing the last two computed results instead of maintaining the entire table. So we can use two variables, previous one and previous two, to store the number of ways to climb the last two steps, that is dp of I minus 1 and dp of I minus 2. Initially, previous one will be equal to 1 and previous 2 will be equal to 2. Now, for each subsequent step I, starting from 3, we can calculate the number of ways as sum of previous 1 plus previous 2. For example, for I equal to 3, it will be 1 plus 2 equal to 3, and shift the variables for the next iteration. That is, previous 2 is equal to 3 and previous 1 is equal to 2. And now we don't need this one anymore. And this is how we will continue up till I equal to n. So continuing for I equal to 4, number of ways will be sum of previous 1 plus previous 2 equal to 5. And we again move the pointers forward. And finally, for I equal to 5, number of steps will be equal to 8, which will be our answer. Now the time complexity of this approach stays O of n, as each step is calculated once in a single loop. But the space complexity reduces to O of 1, as we use only two variables, previous 1 and previous 2. Instead of DP table, in the previous approach. Here is the quick code walkthrough of the algorithm we just covered with Java code on left and Python on right. We again start with the base case, that is, we check if n is equal to 1 or 2, in that case we will return n itself. Now we will initialize the variables previous 1 and previous 2 to 1 and 2 respectively, corresponding to values dp of 1 and dp of 2. These variables represent previous 2 computed values. Now we will iterate from I equal to 3 to n, and for each iteration we calculate number of ways to climb the current step I as the sum of number of ways to climb previous 2 steps, and update previous 1 to previous 2 and previous 2 to the current value. And after the loop, we can return the current value, that is previous 2, as our answer. Interestingly, the recurrence relation for climbing stairs, that is dp of I is equal to dp of I minus 1 plus dp of I minus 2, is identical to the definition of Fibonacci numbers, and the number of ways to climb n steps is equivalent to n plus 1th Fibonacci number. So that's why the solutions we covered in this video were also very similar to the ones we covered in the generate nth Fibonacci number video. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.